I'm going to be showing you how to perform analysis of data recorded from brain, in particular from experiments related to motor imagery based BCIs. As we know, BCIs allows us to interact with external environments such as computer, cursor, or any kind of computer application, or we can even use that BCI interface to control external robotic devices. Well, here I'm just playing one of the demo we did in our lab long time ago, 3 years ago. Subject, this participant, is controlling this circle in 3 directions. Well, as we know, motor imagery BCI requires imagination of some certain limb, such as hand or foot. For instance, in this specific example, he is thinking to move this circle into left direction by imagining his left hand movement, while he's will try to move this circle to the right direction using right hand movement imagination, and upwards is related to foot movement imagination, right? As you can see, we have here some EEG channels, EEG sensors attached to the sensory motor cortex of this participant. So, well, here, okay, you can see some more details. So today, I'll go through some steps of analyzing already pre-recorded data and training a deep learning algorithm with the goal of improving this accuracy, okay, of, for instance, decoding accuracy of EEG patterns related to left hand and right hand imagination. We're not going to be using this foot movement. We will be solving the binary classification problem. You can find this video on my channel. Just type this. I'm gonna give the links in the description. Anyway, so first, I'm going to assume that you are familiar with sensor motor rhythms or motor imagery based EEG PCI paradigm. And another thing is that this video will be much like in a better role. I'm not gonna let's see, edit, improve, and more like a raw video. So what else? So okay, the deep learning library that we're going to be using for training our decoders or classifiers will be based on PyTorch library, okay, and for loading, processing, visualization of EEG data related to sensor motor rhythms will be based on the toolbar called MNE. You can also go there to download it, to import it, or just type pip install MNE. Well, another thing is that there is a very well designed GitHub repository where you can find a lot of datasets, in particular related to, well, motor imagery and many other stuff. You can also check the papers they have published that provides you the more details, okay? So again, go to this website, to this GitHub repo, and try to find, for instance, here, notebooks, pipeline tutorials. Under MOAB and datasets, you can find a lot of datasets the authors have provided. I mean, in particular, the API to download and use this dataset. And all of these datasets come from different laboratories around the world. I mean, this is a very, very good place to get started. All right, so as a benchmark, as a comparison, I will be using some libraries of this brain decode, in particular, the EEG-NET implementation. So another recommendation that I have for you is just read this paper that the authors have published here. They provide the extensive, thorough, research on EEG decoding and visualization. It is open source. I mean, it is on archive. You can download and read the paper. So, well, this is one of the main papers where deep learning has been applied to EEG, and the authors also share the source code. So they provide trial-wise decoding and some different kind of decoding. Okay, so crop decoding and many others. All right, and then yeah, this is the paper. You can go and then read why we're doing, why deep learning is important or could be important for BCI research or in the EEG analysis. So always, okay, read. So now let me go to my Spider Python environment. Okay, so I have installed PyTorch, I have installed MNE, I have also installed Brain Decode. Okay, and I have, in addition, I downloaded 4 different data sets from the mother of BCI benchmark repo. Okay, here, mother of BCI benchmark repo. Okay, I see. Yeah. So mother of all BCI benchmark. Among them, I have, right, okay, so here, so four data sets are known by the following names, and they are located here. So the first data set, second one is here. Its length, not length, but the size is 139 megabytes. Second one is 48 megabytes. Well, PhysioNet is another well-known dataset in multi-major research. It comes from hundreds of subjects. It has 462 megabytes. And then Weibo is another randomly chosen dataset from authors. Okay, anyway, this first 1, 2, 3 is widely used and very heavily investigated dataset in the BCI research. In particular, the first 2, they also come from so-called BCI competition. Okay, that is publicly available online. All right, and I can also share the dataset related to the following video, but not now, not in today's video. Okay, so in today's video I just want to work and explain all these 4 different datasets. So here, dataset information.py, if you look here, provides some information about the dataset. So first dataset, let me put this the other way around. So the first dataset is described as follows. So the following the first dataset is recorded from 9 subjects. It's a queue-based BCI paradigm, consists of 4 different multi-major tasks. And queue-based means you have the queue as you have just seen, just like you have seen on the YouTube video. All right. So that 4 different multi-major tasks correspond to imagination of left hand movement, right hand movement, and both feet. Class 4, okay, the 4th multi-major is tongue movement, okay? And the data has been recorded from 2 sessions on 2 different days. You can also, how many, they have 48 trials, and some other examples. So let's see how many channels they use. Here, 22 channels have been used to acquire this dataset. Again, for the details of experimental paradigm, some more details about this dataset, you can go and review the following paper. Okay, that's highly recommended. And one more thing, I'm just using here all the information shared through, MOA, okay, mother of all BCI benchmark. So second dataset, second one, comes from 9 subjects, 3 channels, very few channels, okay, and also how many class? Let's see, they also have some, okay, multi-major of left hand and right hand. So in this case, we have only 2 classes, but in the following one, we have 4 classes. So what about the 4th dataset, Weibo? Again, here you can find the information more details. So the Weibo comes from a study done in 2014. The author made this dataset publicly available. So the title of the paper is called as follow evaluation of EEG oscillatory patterns and cognitive process during simple and compound link multimetry. Okay, here authors use more dense electrodes, 60 sensors, and 10 subjects. And the last one is known as PhysioNet multi-imagery dataset. You can go find details here, or in one of these two publications. And interestingly, here we have 109 subjects. So, well, VisaNet is one of the data that had a lot of subjects, and also they use 64 channels, 64 EEG electrodes to record the data, and they use a very popular software called BCI 2000 to record, control this stuff. So, all right, I just introduced you. I just gave you a brief introduction to all data set. You can again read later. So let's take a look how they may look like. So first one, okay, 9 subjects, 22 channels, 4 classes. So let me just load it. All right, and then all the data set I have. All the pickles you see here, data is in MNE format. Okay, that is how I saved after downloading from MOAB. Okay, so MOAB doesn't give you MNE format, but I have to change it. So MNE format allows you to visualize, interact with the data set, to perform some exploratory data analysis, things like that. Okay, so let's load first data set. So I'm going to load again, and then let's see here. So len of D means it's a list basically of links, or links 9. So 9 corresponds to 9 subjects. So if I just go to the first subject, index by 0, we will see 2 classes. Okay. Well, this one is already MNE object, segmented dataset. Well, in total, it's not a continuous EEG, it's a segmented dataset around the classes. So we can see in total we have 288 examples or events, also training examples or observations corresponding to left-hand imagination and versus right-hand imagination, divided by half. Okay, and the duration is 4 seconds. All right, so baseline off, all good. So let's see. So now if we just try to let's take the left hand of subject 1, data correspond to the left hand as X, and then try to visualize it. Look, what is good about MNE is that we can visualize the data sets using the methods or the functions provided by the library. So here you see 22 channels, and all these windows denote the links. Okay, the first example is from here to here, 4 seconds. Okay, another 4 seconds, another 4 seconds. We can also visualize so-called butterfly plot. Okay, we're just superimposing all the 22 channels and then visualizing. And 1, 2, 3, 4, 5 numbers correspond to the observed trials. In the machine learning maybe terminology is training example. Okay, 34th training example, 35, etc., etc. And then we see here up to 144. Okay, and multi-major related hidden features are somewhere here in each channel. And our task is to train a machine learning algorithm, deep learning algorithm, to automatically identify those features, patterns related to left-hand imagination or right-hand imagination. All right, so we can also do same thing for, okay, so X again is an MNE object. Okay, so if you just do dir X, you see MNE provides us a lot of, dir X tells us MNE provides a lot of methods, things we can use. Add channels, baseline, apply Hilbert transform, channel names, drop some batch and detrend, some other, so filter, bandpass filter, probably you may want to use bandpass, high pass, low pass. So interpolate bad channels. Okay, if you have bad channels, you can just interpolate on common average bad channels. So you can also pick channels, pick types. So they also provide different plotting functions, okay, for visualization. Well, we can also upsample, downsample, set each reference to different types of montage, and tmin, tmax, and some other field. Okay, so what happens if we try to plot the sensors? Okay, that was our MNE, and then plot sensors. All right, So it shows us the location of the sensors. Right, left, nose. Okay, all the 22 channels, the location of sensors are located here. So if we want to find out about the details, so here, topo map, title, show names. Let's try. I want that information. Show names, true. Okay, now we have information regarding the channel name, CZ. Okay, all that. Okay, no, we cannot do that. So let me go back. So segmented dataset again one more time. You can also load, for instance, this dataset. Okay. Okay, here, right? To also visualize, but here we should expect to have, wait, how many channels? Okay, yeah, so I just missed this one. So we need to use, let's load this dataset. Okay, now 3 channels. Oh, yeah, 1, 2, 3 channels. Okay, second dataset comes from 3 channels. Similarly, FusionNet dataset, and then length of second data 9 subjects. Let's try FusionNet. Okay, we should have 64 channels. All right, a lot of data noisy patterns. Okay, so here all the names of the channel, and then if you want to visualize sensors, okay, plot sensors. But okay, looks like we don't have 3D channel information, but it's okay. So we can still find xinfo. So xinfo shows us the number of channels here, 64. And okay, signal frequency, sampling frequency, 80 Hertz. By the way, okay, this is the information regarding when the data was measured. It's 2009, long time ago. So xinfo ch channel names provides us the names of the channel. Okay. Okay. So anyway, you can find some more information, or you can just explore, perform some EDA, exploratory data analysis. All right. Once you have D as MNE format, and so for EDA, you can just go to the website, find some examples of tutorials, or just let's say glossary, visualization gallery examples. Okay, for instance, since we're dealing with multi-measure dataset, there should be some tutorial examples of visualizing sensor motor rhythms. So you can also take a look, visualize data like this, or perform some time frequency analysis. Oh yeah, here, compute and visualize event-related desynchronization or synchronization maps. All right, and here you can find how you can visualize the dataset. I will show you. Also provides us access to download the FusionNet dataset. And also, you can just click here and just start using it, okay? No big deal. Or Python. So you'll have the example ready and just use your favorite IDE. All right, so, and next step. Let me introduce you the next function. So, okay, train train CNN. So this library, all the source code that I'm sharing is based on CNNs. While, of course, I also provide some LSTM examples, but mainly CNN, okay, convolutional neural network. So here are some import libraries, and then I also provide some data loader. So NU MI data loader, okay, multi-measure data loader. There you have some helper functions that allows you to load the data from MNE format and from this local directory and put it into into appropriate PyTorch tensor. Okay, get torch, EEG data loader, or EasyNet data loader. So if you go to this function, you see the NUMI motor imagery data loader. That also has some scalar standard, normalization that you can apply to your EEG data. Some other helper functions such as augmenting the data augmentation. We know data augmentation is one of the things that we need to do in deep learning, right? Or crop data. So crop data function, or this, we have two different methods. These two are experimental, not the best one, but still, achieves your initial results. So just explore yourself. The idea is based on the brain decode library. You generate multiple, examples, training examples based on what you have, by cropping, define some specific window lengths. In this way, you're increasing number of training examples, which we know that the deep learning library or deep learning models are data hungry. They need a lot of data. So crop training decoding is one of the methods that authors in this paper have proposed to use. So you can also consider or improve this one. It's not probably the best one now, but you can define. Easy data loader loads the data from local directory or local folder directory, let's say, and then extracts two different classes. Here, by the way, target, non-target. Why it is target, non-target? Well, why not left hand, right hand? Because I adopted these codes from my ERP analysis framework, and I was too lazy to rename these into, not too lazy, I didn't have much time to rename this into target, non-target, but target corresponds to left hand, non-target right hand, okay? But at the end, you'll get two class data, as a train, validation, and then X test, and this function, for instance, returns us PyTorch tensors. Well, this one is pooled dataset, okay? The pooled, here let me just clarify what is pooled. So pooled is basically, you have data from 9 subjects, you're creating one pool of the data, right? And then just combining all the data sets and making one pool of data. It's just like treating one huge data set and then dividing into or splitting into X train, X validation, and then X test. Well, another function you can find in MI data loader is the function called subject specific. As a name can say that this function allows us to return subject specific PyTorch tensors. Okay, if you have 9 subjects, you get 9 different data sets split into X train, X validation, and then X test. Well, there are some parameters that you can play around, like the ratio between train and validation. 20%, 10%, it's up to the research, right? So getTorch is another function, helper function, right? Once you have PyTorch tensor, so it allows us to wrap the data using PyTorch loaders, data loaders. You can define batch size, shuffle true or false, and then you get ready data set to be used, to be passed to your training. Again, I assume that you're familiar with the PyTorch environment. You can learn M&E, very simple, but you should be familiar with PyTorch environment to be able to use these codes efficiently. Another function, data EasyNet. Well, EasyNet model, neural network model, requires some different data structure. So as an input, so this function will help you to get that data set in the EasyNet required format. Anyway, these functions were not that optimized, but it works, and if you can further improve it, there are a lot of places for improvement. If you see here, I wrote this like 1 year ago, so I haven't go back and update it. There are a lot of things that you can improve in terms of syntax, etc., optimize the code, but again, I'm passing you what I have, and that can be useful. So next method function that I'm going to be sharing with you is called NU model. NU just stands for, again, Nazarbayev University, and the file has been created again last year, March what you can find here is that flexible CNN 2D CNN model. Flexible, by flexible I mean, right, so you can play, or you can change hyperparameters such as the depth, or the depth of the neural network, how many hidden layers you want to have, how many other parameters, max pool, dropout, batch norm, whatever, some other parameters, for also stride size, for instance here, right, kernel size, and I also provide the function that automatically calculates the output of convolution operator. So mainly you can use this 2D CNN to perform your research as a first step, right? The task will be to find the unique, the model architecture, CNN architecture, that is going to provide us very high accuracy in decoding multi-imagery data set. Specifically here, we have two classes. We want an architecture, right, that will classify left-hand versus right-hand multi-imagery with high precision, and preferably from raw data, using raw data with minimal pre-processing, okay? Also, here you can find LSTM model if you want to use, further. And CNN encoder, and also I provide CNN LSTM. It's a hybrid kind of model, right? You can still use for your model or architecture search. So, and EageNet is the model structure, but however, I'm going to be using the EageNet that has been shared by Brain Decode authors. So another function that I'm providing is called train utilities. Basically, it has just one function that allows you to train your model, right? So train model takes your model, dataset loaders, criterion, right? Loss function optimizer, device CPU or GPU, number of epochs, default 5, bareboat, LSTM, or whatever. So several stages for epoch. First we train, and then validate. Train, and then validate, okay? And for your convenience, it returns the best model, okay? If you run 200 epoch, and your best model is located in epoch, let's say 77, then that best model from 77 is saved here and then returned to you as the best one. And it also returns train losses, some other validation losses, some metrics that you need to generate the results, tables, figures, and also train accuracy, validation accuracy. Well, it's preferred to use not accuracy, but you can change the code to get the AUC metric, okay, area under the row curve, receiver operating curve. All right, so again, dataset information, train CNN, pooled. Here, pooled means, okay, we train CNN on combined dataset from 9 subjects, for instance, or from 100 subjects in PhysioNet case. Train EageNet allows you to train EageNet data structure as a comparison using the Brain Decode library. So here, most of them are here. Okay, here we just use Brain Decode library to get our EageNet. If you open the EageNet structure, this is the architecture you can find. All right, and EageNet is one of them. Another, very popular neural network model for BCI. You can read this paper again. EageNet compact convolutional neural network for EEG based BCIs. It's available on archive. So there are two things. You read the first Brain Decode paper and then EageNet paper. So if you look here, EageNet is located in Brain Decode /models /EageNet. So here, let's see, Brain Decode models. Oh, okay, it's not here. So if you go to Brain Decode models, let me go to the GitHub, Brain Decode. What is that? Oh, I'm just okay. I got confused here. It's not a MOAB, it's brain decode. Decode, find the brain decode. Okay, here GitHub repo. So brain decode models. I just want to show you that the brain decode paper implements some other. So Deep4, another model architecture that they define, you can also use it. So EasyNet, the one we're going to be using, and shallow FSPNet. Okay, you can also use these in your research. But first, you need to read this paper thoroughly. Okay, you have to read these paper. Deep learning with CNN, PyEG, decoding visualization, and then go to the source codes and then try to modify, improve, or reproduce the results of the authors. Okay. So, all right, let me just take a pause. So, EasyNet, train EasyNet pooled, train CNN pooled, and I should have train CNN subject specific. All right, so train CNN in pooled basically just loads all the data. Okay. I have the following. Okay, GPU. And okay, if you don't have GPU, then unfortunately you are very limited. Okay, but if you have GPU, then you're lucky. Otherwise, as an alternative solution, try to use Google Colab. Google Colab, well, it's a bit slow, but if with your patience, you can still run these codes on Google Colab. Okay. All right. Anyway, we're not dealing with million examples, so Colab should be feasible. All right, for research. Okay. Import Torch, Pandas, Pickle, NumPy, their tools, easy data loader train model. Okay. CNN, this is the model architecture that we're going to be using. So import, get data. We define all 4 datasets located here in the local directory. And you define number of epochs. Let me just run one epoch, okay? Just for you to show. Usually it should be around 200 or something like that, okay? So one epoch, learning rate, weight decay, batch size, 64, okay. And augment data, it's another argument so that you pass to your data pool. So data pool, okay, will, if it's provided, will perform some augmentation. So none means don't do any augmentation. So 1 means, okay, 2 means some multiple of the data set, multiplied data. And we need to define sampling frequency, 80 Hertz, for performing cropping. Okay, true. Yeah, and another parameter, countdown true, it's related to architecture. And then here class 1, 2, we call it as left hand, right hand. And S is, I just create a long list of, subject placeholders for loop for iterating. So, okay, the main loop starts here. We get, for each data set, we get step by step for perform modeling first data set, second, right, third, and then fourth. Basically, the training appears here, in a batch form. So this function, just run, all the training should be done for each, and then all the results should be saved separately. Okay, so if I run easy data loader, pool, okay, pandas for saving train validation test accuracy, you get the data. This is the data set that you're going to be passing to your model. Time length, chance, input size. Okay, here, the convolutional neural networks have this kernel size hyperparameter. In most cases, in image recognition tasks, they use square shaped kernel size, but each is not square. So you can try rectangular. So 3 by 1 means basically 3 by 1 kernel size defines here. So 3 and A1 and then current time. This second number corresponds to the temporal features. So by default, this is all right, corresponds to 100 milliseconds and 300 milliseconds and 500 milliseconds across time points. And then across channels, we have 3, 3, 3 fixed. You can, again, try different combinations, okay? And here, conf channel. So conf true, conf down true means the first will perform, we will perform conf down true, a model selection using a different combination of CNN architecture. Here, 16 corresponds to 16 feature maps in the first convolution layer, 8 feature maps in the second conf layer. So we increase the number of layers as we go down. 2 conf layer, 3 conf layer, 4, 5, and then we can go as deep as 6 convolution layers. You can again try to, if you're not succeeding, you can try to increase one more time. By one more conf layer. All right, I don't know what. Okay, so now we have 1, 2, 3, 4, 5, 6, 7. CNN architecture with 7 convolution layers, and then for full connected layer we use just fixed one fully connected layer. Okay, one size 1. Then once you're done with this conf down true, you can try false. Okay, that will allow you to try different other type of architectures. So here it's increasing, so different patterns. As we go deeper, layer 5, we have more feature maps there, right? Well, here the question is which type of architecture can learn hidden features in a hierarchical form using convolution layers. So we pass those parameters and we loop across all each. So first we define this, okay, architecture, and then get the dataset description. Well, here we define the model architecture right here. We're passing input size, all right, consists of channels and time lengths, and we're passing the D kernel size. So D kernel size corresponds to one of these. Second, D conf channels. So in the first case, we tried these conf channels, another. So, and then for each, we use this model to instantiate, and our optimizer loss function, we use cross entropy. We move to device, okay, to our GPU device. Forget about running this on CPU. You'll not succeed. It'll, most probably crash. And then we pass these model and criterion to our trained model. Train, it's just, train function. It just takes a model and then performs training, validation, and we returns as best model, and train, validation, loss, accuracy, and other information. Okay, and you use that best model on the fly. You can test. So get the X test from this data set that you have already, already beforehand saved, and then use this model, okay, to predict what it, these test samples correspond left hand, right hand, and you can calculate the accuracy right here. Okay, that corresponds to test accuracy, and then you can report. Actually, another way would be, okay, instead of testing this on the fly, first save your model. Save your model in your hard drive. Second, once you're done with load it and test it on test examples, okay, don't do it on the fly. However, here I'm just showing one example. And test samples means, depending on your computational power, you can pass 500 tests, 5,000 if you have enough, 5,000, or 100 if you're having some trouble, you can just try 150. Okay, sequential, and then generate results. So table results, okay, is saved here, okay, and we can use these in and pull, etc., and dump all the results and use to generate, to produce some results for further analysis, see if it works or not. So let me try to run, and I know it will take time. So once you run this one, okay, here what is happening. First architecture, CNN of the following, okay, architecture hyperparameters. Let's see, okay, it's quite fast. So 16, 8, 2 conf layer, 16 feature maps, 8 feature maps, kernel size. This is a rectangular kernel size. This is height and then length, okay? Flattening output model architecture again. We use maxful and drop out by default. You can try to change these parameters again. And 2 fully connected layers, okay? And then we see them accuracy, training accuracy, validation, test accuracy. And then the model, I mean, where in the epoch the best model is located. Looks like here in the first epoch. And okay, try again. Same architecture, but different kernel size, okay? These are different hyperparameters. I see some error popped out. Okay, so first, same architecture with different kernel size. More deeper conf layer, 3 conf layer with different parameters. We see that, all right, as we go deeper, we see the test accuracy is increasing. See if you compare these column. But surprisingly, the best model is located in the first epoch. You can do some sanity check, try to change learning rates or some initialization, weight initialization before running. All right, and then what we have here is as we go deeper. Okay, so here we have some problem with the dimensionality, so we can fix it. To fix that, I'm going to go to CNN model. All right, and then max pool. Okay. Just maybe because let's try it. Now let me try again. Okay, just I know that's not the best way of doing things, but okay, all this has been saved. I'm just going to yes to all. One more time. Okay. Oh, okay. Number of epochs. I'm setting it to 1. That's why. But usually you set it to 250. Okay, just for demonstration purpose, just pass 1 epoch. Up. Okay, crop lengths. I'm just making the crop lengths of, because the entire window is 4 seconds. Here I'm just cropping with the window length of 1.5 seconds here. Now let me try to run this again. Hopefully the error should not happen. Okay, so you need to wait until all the training is complete, and it may take some time depending on your computation power, whether you have GPU or not. So far I can see that the model with the highest test accuracy is 74, but of course we don't just rely on test accuracy, we need to look at the validation and the difference between training and validation. So validation accuracy is used, it's helpful to select the best model. All right, so now we are moving into the second data set. So look, we have first table. You can use this to summarize your deep learning model selection journey. But again, change these epochs to not 1 but 250, then you should have different results. You should expect to have different results. And there's so many parameters, so many things that you need to consider while doing your deep learning research, right? All right, things like this. So I'm going to cancel it. So what you will have here at the end is all the files saved, okay? So 50, the last one corresponds to test accuracy. These numbers correspond to number of, neural network architecture, 8, 16, 32, increasing, okay? So here we have 6 layered convolution. All right. And then once you're done with BNCI here, second data set, okay, all the BNCI, and then Weibo. And then later comes the FisioNet. well, all your data set is saved in this file. This is a pandas data frame where you can go back and do some summary. And by the way, these are the best models. These files correspond to your model with the weight saved. Okay, you can load them again, use it in in real-time BCI if you want. So let me delete all these. All right. So let me see alt X. Okay. All right, that was an easy pull. And then once you decide what architecture looks good, you can go to subject-specific modeling. In subject-specific modeling, you do similar thing, but you have a model that should be tested on each subject. Okay. All right. So let me show this. Oh no. Okay, just delete this. We don't need this information. And we import again CNN, augment data or not. Okay. 1, 2, 3. What we have here? The loop. Oh yeah. Here you need to define dataset specific neural network architecture. So BNCI 4004, for instance, have 9 subjects. Okay. If item name is BNCI, this one, your final architecture should have, for instance, convolutional channels with the following, convolutional layers with the following architecture: 64, 32, 16, 8, something like that. Okay. You can do some other stuff, weight initialization, yes, some other experiments, but I'm just gonna go and yeah, you can also do augment, crop, augment, yes, right? Let me just delete this and see if it helps, right? Perform crop training or not. I just did by default crop training to all of them, okay, beforehand, and also augment for all of them none, but you can just delete this and then decide data specific crop training or augmentation. Okay. What else? Okay, and also the kernel size here. Yeah, again, these are data specific ones and it can change, right? Or you can just declare global regardless of the data type, kernel size and convolutional neural network architecture, just global one. I mean the best one, which is which works across all different data sets. Okay, so let me just crop, and again crop. Okay, crop takes these parameters and decides whether to crop or not. And data specific will have the following parameters like normalize, true or not. So normalization using the scikit-learns. Let me see. Okay, this function. Okay, we use standard scalar to perform some normalization. Okay, go back. Time. The remaining parts are pretty much same. You can just all the same. Okay, very similar. But here, as compared to pooled one, you'll get data set specific results. Subject specific results. So again, pooled, subject specific, and train EageNet. Okay, train EageNet pooled. Well, we don't have to do EageNet pooled, but you can try. But we are interested in EageNet subject specific. Okay, you can import EageNet structure like here. Define the dataset in local directory and number of epochs, learning rate, weight decay, and load pooled, and perform similar. So most of them are very similar. The steps that I describe here are very much similar for CNN, EageNet. Okay. What else? EageNet subject specific. I should have it somewhere. Let me see. Why I don't have EageNet subject specific here? All right. Where is? EG subject, EG net subject specific. What is it? Train EG net. Okay. So yeah, you can also basically just go through these steps. The only thing that's going to be different is that instead of CNN 2D, you're going to have EG net, okay, here. And EG data loader will be different. Okay, in this case, EG data loader. That will load EG data loader. Here. So yeah, only the difference will be the get data will be get data EG net. Okay. So you need to make sure that you define this get data in this case. Not from PyTorch get data, but from here. Okay. So try to perform subject specific for EGNet. I had the script somewhere, but I can't find. But the only thing is that you need to replace get data, but for get data EGNet, and of course the model will be EGNet model that you will use from here. Okay. All right. So why I don't have that thing? All right. Let me try to find. Train EGNet. Train augment. Train augment. Train EGNet. Okay, I think I have it. Okay, where was that? Where was that? EGNet, train EGNet. Subject specific. Well, again, okay, if I find it, I'm gonna put it somewhere and then share with you, but you get the basic idea. You just need to change CNN subject specific to train EGNet subject specific. Pretty easy. And some final thoughts. So any models that Pi has LSTM model, okay? Try to perform LSTM model selection, all right? Or the hybrid CNN to LSTM model, okay? CNN LSTM model selection, try to perform. So let's see hybrid CNN LSTM, how it may look like. Okay, so hybrid CNN, there was one famous structure, CNN. Yes, something like this. So first layers will correspond to CNN, and then you just use CNN as a feature extractor and LSTM as a decoder. All right. Okay. I guess that's it for today. Let me know if you have some questions regarding these codes and analysis, either by sending an email or leaving a comment on the GitHub, however comfortable for you. So I think that's it for today. And yeah, again, one of the research, just at a very high level, the research question would be, can I come up with a novel CNN-based architecture that will give us highest accuracy in decoding human mental state, that mental state which corresponds to, either moving right hand, left hand imagination. So if you come up with a model and then deep learning architecture, you can just imagine that this ball will move to this direction at a very higher speed and with a high precision, and you can use this binary class to control, let's say, lower limb exoskeleton, just binary, comment left, and some other examples, right? The application will depend on the need of the user. That's it for today. Thank you for your time. I'm going to put this on YouTube right, as a reference. So so that you can come back, watch it again, and contact me if you have questions. I'm not going to edit this video, just leaving it as it is in a raw form. See you around.